Welcome you all in this Cryo-EM course. So today we are going to discuss about different component of electron microscope. Especially today our major focus will be electron gun, and the next lecture will be electromagnetic lenses. So first we will focus on electron gun. Before discussing about electron gun, we should know rest of the component of our microscope. So we already discussed about this slide in last class, that what is the schematic diagram of this microscope. If you look at this inner side of this microscope, you can see that okay, there is an electron gun, and then there is an anode, and then there will be a two lens. Lens name is called condenser lens 1 and condenser lens 2, and additionally, so there will be another condenser lens, that is called condenser lens 3. Now if you look at, this is the objective lens where our sample will stay. This is called the stage of the microscope. Here if you want to connect with that stage or goniometer, this is the stage or goniometer, and the same part we are showing the inner part of the microscope, where you can see there is a two objective lens. So upper objective lens and lower objective lens, that we are going to discuss more. Now if we look at that, after this one, when specimen will interact with the electron beam, it will go through the intermediate lens and projector lens, and finally it will give us an image here on the fluorescent screen. Now that is a very simple schematic diagram. Now we have to connect those component with our microscope. So it will be easier for us whenever we will go to the microscope room, we know which part we are talking about. So now you can see this is a microscope, where this is an electron microscope, if you just specifically tell that. So here you can see this is a 200 kV microscope, TechNI or FEI made, and this is the schematic diagram of this electron microscope. Here at the top part of this microscope is connected with our high tension. Previously I mentioned that we are talking about 120 kilovolt microscope, 200 kV microscope or 300 kV microscope. So that kV, that 300 kV or 200 kV high tension cable will connect through this particular region, where that cable will go and connect with our filament. Now if you look at inside the filament, what do you have? The filament has a three different component. So this is called the electron gun. So that electron gun, it has a filament, then it has a V-node cylinder. This V-node cylinder is very important. We will draw and explain it why V-node cylinder is very important, and then there will be an anode. This anode, so electron will come, and this is called the optical axis, which is going through the center part of the microscope, this line. Now after anode we have a gun deflector. After gun deflector we have condenser aperture and condenser lens system. So now you can see there is a two condenser lens system is there. There is a condenser lens 1 and condenser lens 2, and for 300 kV microscope we have one extra condenser lens, that is called the condenser lens 3. Then again there will be a beam deflector, then objective astigmator, then objective lens. So as I mentioned in last schematic diagram, we have a lens system which is called upper objective lens and the lower objective lens. So here there is it is splitted into two lens system, that upper objective lens and lower objective lens. Then it will come to image deflector. After that intermediate lens, diffraction astigmator, then projector lens 1 and projector lens 2. Now how do we connect those things? If I just consider that okay, condenser aperture and condenser lens system is connected here, then condenser 2, then our sample holder, this is our objective lens system is connected here, and then objective lens aperture and selected area aperture, whatever we have, the objective lens aperture and selected aperture which is connected here. This is, I mentioned that this is the goniometer which is showing it here, and this is our sample holder. The sample holder will be almost more than 1.5 feet long rod, where sample will stay inside, sample will stay where the optical axis is. Now this is the same viewing chamber, and we have two binocular. Through this binocular we can monitor these things, and this microscope is connected with a computer where we have a CCD camera or a plate camera or a direct electron detector which is connected with a computer, and it will give us image directly. So these are the internal component of that microscope. Now one important part is that the fluorescent screen, is mainly made by zinc sulfide and cadmium sulfide powder. This is a fluorescent screen. When electron beam will interact here, it will give us a green light, and we can see the sample, the 2D projection of a 3D object in this screen. Okay. So electron gun, we are going to discuss about the electron gun, what kind of electron gun we have. So specially we can split that electron gun into two hubs, that one is called thermionic emission or thermionic cathode. It is a tungsten hairpin filament or pointed lab 6 rod, and the point source cathode, that is called the Schottky emission or field emission. So initially we are going to discuss about these two electron gun at the beginning, and then we will discuss about the electromagnetic lens system. So any microscope, if we just want to think about that, okay, what elements of do we have in our transmission electron microscope, it will start from at the top, it will come as electron gun, and then electromagnetic lens, and then column, knobs and their name. Definitely that is important, because in our microscope you can see there are total 6 lenses are there, electromagnetic lenses, and that is a very complicated system than light microscope. If you just consider the light microscope, 2 lenses or 3 lenses are good enough, where you have a eyepiece and then you have a 3 or 4 objective lens and combine this and you are getting an image here. But in this particular case you can see there are total 6 electromagnetic lens system is there. It will be better to remember that what kind of electromagnetic lens do we have. So for that reason a easy schematic diagram, it will be always good. So if we just consider, we will always say, okay, we have a electron gun always. So this is an electron gun. Then we are getting, first thing that we will get the anode here, and then after that we will get the condenser lens 1 and condenser lens 2. So electron beam, first it will converge somewhere, converge in somewhere here, and then it will go through the first condenser lens 1. This is the first condenser lens and this is the second condenser lens. So we will use a ray diagram where it will converge. So whenever we have a lens system is always doing this, it is converging the electron beam and diverging the electron beam. So this is called the converging electron beam, and then again if it will go fast, this is called the diverging electron beam. This is diverging electron beam, this is the converging electron beam. Now this is the point is called the focus point, or you will say the crossover point. Crossover. Okay. crossover point. So, this crossover point, that wherever the electron beam is converged in one particular point, we will tell this is a crossover point. So, now for the condenser lens 1, so we are getting a crossover point somewhere here. Then next again there is a condenser lens 2, it will converge the electron beam somewhere here. Then it will just go like that, each and every step there will be electron beam will converge, and finally it will give us an image here. So, in the next step this will be our objective lens. Okay, then definitely our intermediate lens and projector lens. So, here what is happening, electron beam will always converge and diverge, and this crossover point it will vary. So, in this particular case you can see that different lens system, we are not using or changing the lens, we are just changing the magnetic field of this lens, and we are just changing the crossover point of this particular lens. We will talk about those part when you will discuss about the electromagnetic lens, but this is a schematic diagram where you can see that how this converge and diverge thing is happening. Here this should be our optical axis, definitely this should be always the straight line. Okay, so now we will discuss about the electron gun. Before going to talk about electron gun, couple of important points we should focus and we should know about those. So, here we are always using the electron gun, means we have a filament and that filament has some metal, say it is a metal component. So, that metal component, what we have to do from the metal component, we have to extract that electron, and it is not an easy task that when we have a metal and you have to take out electron from the metal. So, if there is a metal surface, if you just consider, so there will be some loosely packed electron near the surface. Now, we need some kind of energy, it may be the vibration energy, or it may be the electrical energy, or it may be the heat energy, or maybe the light energy is required to displace that electron from the metal. When that electron will be displaced from the metal ion, so there will be a charge difference between the metal and the electron, because electron just came out from the metal. Okay, and due to this charge difference, the metal, it will attract that electron again, and the electron will go back to the metal. So, electron cannot detach from the metal easily. So, what is required? We need a minimum amount of energy, it may be heat energy, it may be light energy, minimum amount of energy where electron will detach from the metal, and it has enough energy, it has no velocity, and it will not going back to the metal ion. So, if we can extract that electron from the metal ion, that will really help us to make an electron gun, because then we can use some kind of accelerator voltage, that electron is detached from the metal ion, and now there is a system which can pull out this electron from the metal, and we can make an electron gun. So, when we are talking about that, okay, we have a metal surface and we have to detach that electron, and we need an energy. At the same time, that metal also has some kind of force or energy which is trying to keep that electron. That is called the work function of the metal. So, here there is a definition that what is called work function of the metal. So, the minimum amount of external energy is required to extract free electron from the surface of the metal is called the work function or threshold energy. The work function of a metal is measured by electron volt. So, here the 2 points we have to pay attention, that minimum amount of energy required, and that energy should be external energy. It may be a heat energy or some other form of energy. In this particular case, for the electron microscope, we are going to use the heat energy. That is the reason we mentioned that it is a heat energy. Now, extract free electron from the metal surface. Okay. So, this work function metal is measured as a electron volt. Now, low work function, less amount of heat energy is required to remove the free electrons from the metal. The metal with a low work function emits large amount of electron at high temperature. So, there is a low work function or high work function. Some metal has this kind of tendency, they have a loosely packed electron, and if you give the sufficient amount of heat energy, it will release a huge amount of electron. So, we need a metal ion like that which can release a good amount of electron which we can use for electron gun. High work function is required a more amount of heat energy to extract the free electron from the metal. High work function emits less number of free electron at high temperature. So, electron emission from the metal surface depend on the strength of the electric field near the metal and work function of the metal. When metal is heated sufficiently, its free electron gain enough kinetic energy to leave the metal. This process is called the thermionic emission, because if you remember first time what I told, there is a two types of electron gun we are talking about. One electron gun, it is called thermionic emission, and other electron gun we are talking about Schottky filament and field emission gun. So, that when we are hitting the metal energy, what is happening? There is a free or loosely packed electron, they are gaining enough kinetic energy, and when they have enough kinetic energy, they will leave the metal. So, here we are using the heat energy to remove the electron from the metal. That is the reason it is called thermionic emission. So, work function we denoted by this symbol, that is called phi W. So, minimum energy is required to remove an electron from the surface of the metal, and electron will come out without any velocity. So, as I mentioned, when there is a metal, we are giving some energy, electron will come out, electron will not go back to the metal because it has sufficient energy, but its velocity will be 0. Now, we have a anode which will pull out this electron towards the other length system. So, that is very important here. Now, there is a very basic formula we are writing here. It is not mandatory that you have to remember all this formula or mathematical derivation or physics behind this formula, because this is the microscope course mainly focusing on the biological application, but it is good to know what is this work function, how we are making an electron gun. Even biologists are using this electron microscope. So, this is something that you know your equipment, you know your microscope first before you start doing your work. So, here there is what is the relationship between that potential energy of metal and then electron, and electron is coming out and their work function. If we consider the relationship between this metal ion, is here the potential energy. Here the potential energy Vz of an electron in front of a conducting surface at a z distance which is larger than the atomic diameter. So, here this is the potential energy of an electron. Here this is I mentioned, this is the work function, and then which is minus by E square by 16 pi epsilon 0 multiplied by 1 by z, and minus E modulus of electric field and the z. Z is the distance which is larger than the atomic diameter. So, why we are talking about that larger than the atomic diameter? Because electron, when it is staying inside the metal, within the metal, so it is within the atomic radius or atomic diameter. Then electron is detached from that, and it is not within the atomic diameter anymore, and that is the reason we are talking about the distance z should be larger than the atomic diameter. Now, this is the relationship between the potential energy and the work function. Now, we want to draw a diagram and want to see it how this thermionic emission is happening and what is the relationship with the work function and other system. So, based on our electromagnetic lens system or electron gun system, we have majorly three different classification. That three majorly different classification, we can classify it like that. Here if we have electron gun, we can classify these things into three major classes, that thermionic emission, then the next one, it is coming Schottky emission, and then field emission gun. So, here this will be denoted as field emission gun always. Schottky, specially it is mentioned that XFEG, and thermionic emission mostly we say W or tungsten filament. So, this thermionic emission also we can tell that there is another type of thermionic emission we can use it, that is a crystal. This crystal name is Lab 6, it is called Lab 6, means lanthanum hexaboride crystal or cesium hexaboride. So, this thermionic emission we can keep it like that, it will be either tungsten filament or Lab 6 filament, then it is coming Schottky, XFEG and the field emission gun. What is the relationship between these three different types of electron gun? So, let us take a look how this electron gun is working. So, if we look at now with our work function, what is the relationship between the work function and all these three types of electron gun. So, if we just consider that okay, here we have a metal, this is the metal surface. What I told already, that metal surface you need some kind of energy which will allow your electron to detached from the metal ion, detached from the metal, and then it will get some kind of velocity. So, I will just draw a line something like that which will help us to draw rest of the thing. So, the work function of this metal you just consider YW. So, you just consider this is the for tungsten filament we are drawing at beginning. So, then electric field, this is the metal, this is called vacuum. This is the vacuum. So, now if we are allowing the energy, we are giving the heat energy to extract that electron. So, I will just use a different color here, maybe red. So, in this one, in thermionic emission, what's happened? Thermionic emission, we need this much energy to take out the electron and make that there is no speed of that electron. So if we just look at this red curve, this is, we'll get a curve like that. This is called the thermionic emission. Okay, so this is called the thermionic emission, and you can see, so here the energy barrier is really very high. So you need a huge amount of energy, heat energy, to heat that filament to extract that electron. So for thermionic emission, one good example is tungsten filament. So most of the time we are using tungsten filament to heat that filament. Now tungsten filament, if I write that value, you can see it that for the tungsten filament, what is the energy or heat energy it is required? You can tell that it is almost 2500 to 3000 Kelvin heat energy is required to overcome that work function of the tungsten filament and then extract that electron from the metal ion. So here the next step, one more thing, that melting point of the tungsten filament, if we just consider that Tm of the tungsten filament will be 3650 Kelvin. So now here one point we all should remember that we are using a huge amount of heat energy to extract sufficient amount of electron, and that sufficient amount of electron is helping us to give us the brightness there. Now the melting point of tungsten filament is almost very close to this 3000 Kelvin, where melting point is 3650 Kelvin. So chances are very high, if you just use 3000 Kelvin heat, the filament will reaching near the melting point of this filament, and filament will degrade very fast. That is one of the major drawback of the tungsten filament or thermionic emission, because you need a huge heat energy to extract that electron and overcome this work function of that metal, and then you can extract that electron and you can extract that electron, and electron can travel through the column. So that is the reason, you know, this tungsten filament or thermionic filament damaged very quickly. So if we just consider that work function, what will be that value? It will be almost 4.5 EV. Okay. Now what about the other? So now I will use a different color and I will show you that, okay, for the Schottky emission you will get a similar kind of curve. You will get a similar kind of curve that it will go through this, and then there is a change in their path and it will go like that. So this is called the Schottky emission. Okay, and you can see there is some change in the work function, that definitely it reduce the work function suddenly, and if we just consider there is a change, if this is the actual one, you can see some kind of changes is there in the work function, and that I can denote like this one. So in Schottky emission there is a change in the work function value. What is that value? It will be something like that, 2.7 EV. Okay. So in this particular case, that Schottky emission, if you just consider that you need heat energy again to extract that electron, but definitely that heat energy it will be lesser than your thermionic emission. Heat energy it will be somewhere, you know, if you just consider 1400 to 1800 Kelvin. for Schottky. So, good thing is that when you are using this much energy, you are not damaging the filament, you are not very close to melting temperature of the filament, but it is decrease the temperature. So, it is not destroying the filament, as well as it is beam will be much more coherent if you are not using very strong heat energy. Now, I will draw the final one for the field emission gun. Field emission gun, if we just look at, so it will go something like that. If you just draw, then definitely there is a work function value is changing. So, in this is called the field emission gun. Now, what component do we have for the Schottky emission as well as the field emission? We are going to discuss about this, how they are different than our thermionic emission. But definitely if we just look at here, work function is much lesser for Schottky, and even field emission gun, it is a much better than Schottky as well as the tungsten filament. That is giving us a more coherent electron beam. What we discussed last class also, that coherent electron beam is very important because they are all in same phase, same amplitude and same path. And this coherent electron beam, it will give us a better contrast as well as the better images, and we can restore the high frequency signal from this coherent electron beam. And that is the reason this, to get a very coherent electron beam, the Schottky filament or field emission gun is a better choice than tungsten filament, because whenever there is a heat energy, the expansion of the filament tip will be there, that is going to affect our coherent property of that electron beam. Okay, so rest of the part let us discuss in the next class. I'll thank you all for your attention.